Hi friends, now we are discuss about real number. It is 10th chapter of mathematics. Let's begin. Real number. Introduction. In class 9, you began your exploration of the world of real number and encountered irrational number. कक्षा 9 में आपने रियल नंबर और irrational नंबर की जानकारी ली होगी. We continue our discussion on real number in this chapter. हम इस चैप्टर में रियल नंबर के बारे में बातें करेंगे. We began with two very important properties of positive integers in section 1.2 and 1.3, namely the Euclid's division algorithm and fundamental theory of arithmetic. हम जो है यूक्लिड डिवीजन एल्गोरिथम और फंडामेंटल थ्योरी ऑफ अर्थमेटिक के बारे में बात करेंगे. Euclid division algorithm, as the name suggests, has to do with divisibility of integers. So how many x were there? Let us try and solve the puzzle. Let the number of x be a, then working backward. We said that a is less than or equal to 150. Counted in 7, nothing will remain, which translate a is equal to 7p plus 0. For some natural number p, if counted in 6, a is equal to 6q plus 5. If counted in 5, 4 will remain. It translates to a is equal to 5r plus 4 for some natural number q. If counted in 4, 3 will remain. It translates a is equal to 5s plus 3 for some natural number t. If counted in pairs, 1 will remain. It translates to a is equal to 2u plus 1 for some natural number u. That is, in each case, we have a and a positive integers b. In our example, b takes value 7, 6, 5, 4, 3, 2 and respectively, bracket close, which divides a and leaves the remainder r. In our case, r is 0, 5, 4, 3, 2 and 1 respectively. That is similar than b. The moment you write down such equation, we are using Euclid division lemma, which is given in theorem 1.1. Getting back to our puzzles, do you have any idea how you will solve it? Yes, you must look for the multiple of 7 which satisfy all the conditions, but trial and error, you will find he had 119x. In order to get a feel for that Euclid's division lemma is, consider the following pairs of integers 7, 6, 5, 12, 20 and 4. Like we did in the example, we can write the following relationship for each such pairs. 17 is equal to 6 into 2 plus 5. 6 goes into 17 twice and leaves the remainder 5. 5 is equal to 12 into 0 plus 5. This result holds since 12 is larger than 5. 20 is equal to 4 into 5 plus 0. Hence, here 4 goes into 25 times and leaves no remainder. That is, for each pair of positive integers a and b, we have found whole number q and r satisfying the relation. A is equal to bq plus r, where 0 is equal to or smaller to r and r is always bigger to p. Not q or r also be 0. Why don't you now try finding integers q and r for the following pairs of positive integers a and b? An algorithm is a series of well-defined steps which gives a procedure for solving a type of problem. The word algorithm comes from a name of 9th century Persian mathematician Al-Khwarizmi. In fact, even the word algebra is derived from a book he wrote called Hisab al-Jabr wal Mukawala. A lemma is proven statement used for proving another statement. Euclid division algorithm is a technique to compute the highest common factor SCF of two given positive integers. Recall that SCF of two positive integers a and b is the largest positive integers d that divided both a and b. Let us see how the algorithm works through an example first. Suppose we need to find the SCF of integer 4, 5, 5 and 42. We start with the larger integer, that is 455. Then we use Euclid's division to get 455 is equal to 42 multiplied by 10 plus 35. Now consider the divisor 42 and remainder 35 and apply the division lemma to get 42 is equal to 35 into 1 plus 7. Now consider the divisor 35 and the remainder 7 and apply the division lemma to get 35 is equal to 7 into 5 plus 0. Notice that the remainder has become 0 and we cannot proceed any further. We claim that SCF of 455 and 42 is the divisor at this stage 7. You can easily verify this by listing all the factors of 455 and 42. Why does this method work? It works because of following result. So let us state Euclid's division algorithm clearly. To obtain the SCF of two positive integers, say c and d, where c is greater than d, follow the step below. Apply Euclid's division lemma to c and d. So we find whole number q and r such that c is equal to dq plus r, while 0 always equal to or less than remainder and remainder is always less than differentiate. Step number 2. If r is equal to remainder means is equal to 0, d is the SCF of c and d. If r is equal to if r cannot equal to 0, apply the division lemma to d and r. Continue the process till the remainder is 0. The divisor at this stage. This algorithm works because SCF C and D of is equal to SCF of D and R, where the symbol SCF CD denotes the SCF of C and D, etc. Example 1. Use Euclid divisions algorithm to find the SCF of 4052 and 12576. Solution. Since 12,576, 4,052, we apply the division lemma to 12,576 and 4,052 to get 12,576 is equal to 4,052 into 3 plus 420. Step second. Since the remainder 420 cannot equal to 0, we apply the division lemma to 4052 and 420 to get 4052 is equal to 420 into 9 plus 272. We consider the new divisor 420 and the new remainder 272 and apply the division's lemma to get 420 is equal to 272 into 1 plus 148. We consider this new divisor 272 and new remainder 148 and apply the division lemma to get 272 is equal to 148 into 1 plus 124. We consider the new divisor 148 and the new remainder 124 and apply the division lemma to get 142 is equal to 124 into 1 plus 4. We consider the new divisor 24 and the new remainder 4 and apply the division lemma to get 24 is equal to 4 into 6 plus 0. The remainder has now become 0, so our procedure stops. Since the divisor at this stage is 4, the SCF of 12,576 and 4052 is 4. Notice that 4 is equal to SCF bracket 24 comma 4 bracket close is equal to SCF of 124 and 24 is equal to SCF of 148 and 124 is equal to SCF of 272 and 148 is equal to SCF of 420 and 270 is equal to SCF of 4052 and 420 is equal to SCF of 12,576 and 4052. Euclid division algorithm is not only useful for calculating the SCF of very large number, but also because it is one of the earliest example of an algorithm that a computer had been programmed to carry out. Remark: Euclid's division lemma and algorithm are so closely interlinked that people often call former as the division algorithm also. Although Euclid division algorithm is stated for only positive integers, it can be included for all integers except 0. B cannot is equal to 0. However, we shall not discuss this aspect here. Euclid division lemma algorithm has several applications related to finding properties of number. We give some example of this application below. Example number 2. So that every positive even integer is of the form of 2q and the every positive odd integer is of the form 2q plus 1 where q is some integers. Solution: let a be any positive integers and b is equal to 0, then by Euclid's algorithm a is equal to 2q plus r. For some integers q equal to or less than 0 and r equal to 0 or r equal to 1. Therefore, 0 is less than or equal to r and r is less than to 2, so a is equal to 2q or 2q plus 1. If a is of the form 2q, then a is an even integer. Also, positive integers can be either even or odd. Therefore, any positive integer is of the form 2q plus 1. Solve example 3. So that any positive odd integer is of the form 4q plus 1 or 4q plus 3 where q is some integer. Solution: let us start with talking a. Where a is positive odd integer, we apply the division algorithm with a and b is equal to 0. Since 0 is less than or equal to r and r is less than 4, the possible remainder are 0, 1, 2, 3. That is, a can be 4q or 4q plus 1, 4q plus 2, 4q plus 3, where q is the quotient. However, since a is good, it cannot be 4q or 4q plus 2. Therefore, any odd integer is of the form 4q plus 1 or 4q plus 3. Example 4. A sweet seller has 420 kaju barfi and 130 badam barfi. She wants to stack them in such a way that each stick has the same number and they take up the least area of the tray. What is the maximum number of burpee can be placed in each stick of this purpose? Solution. This can be done by trial and error, but to do it systematically, we find a CF of 420 and 130. Then this number will give the maximum number of burpee in each stick and number of stick will then be the least. The area of tray that is used up will be the least. Now let us use algorithm to find the SCF. We have 420 is equal to 130 into 3 plus 30. 130 is equal to 30 into 4 plus 10. 30 is equal to 10 multiplied by 3 plus 0. So SCF of 420 and 130 is 10. Therefore, the sweet seller can make a stack of 10 for both kinds of burfi. Fundamental theory of arithmetic. In your earlier class, you have seen that any natural number can be written as a product of its prime factor. For instance, 2 is equal to 2, 4 is equal to 2 into 2, 253 is equal to 11 into 23, and so on. Let us try and look at natural number for the other direction. That is, can any natural number be obtained by multiplying prime number? Let us see. Say 2, 3, 7, 11 and 23. If we multiply sum of all these numbers, allowing them to repeat as many times as we wish, we can produce a large collection of positive integers, in fact infinitely many. Let us list a few. 7 into 11 into 23 is equal to 1771. 3 into 7 into 11 into 23 is equal to 5313. 2 into 3 into 7 into 11 into 23 is equal to 10,626. 2 power 3 into 3 into 7 power 3 is equal to 8,232. 2 power 2 into 3 into 7 into 11 into 23 is equal to 21,252, and so on. Now let us suppose your collection of primes includes all the possible primes. What is your guess about the size of this collection? Does it contain only a finite number of integers or infinity many? In fact, there are infinity many primes. So if we combine all these primes in all ways, we get an infinity collection of numbers, all the primes and all possible product of prime. The question is, can we produce all the composite number this way? What do you think? Do you think that there may be a composite number which is not the product of power of primes? Before we answer this, let us factorize positive integers, that is, do the opposite of what we have done so far. We are going to use the factor 3 bit which you are all familiar. Let us take some large number, say 32,760, and factorize it as shown. 32,760 if we divided by 2, then it is 1600, 380, and again divided by 2 it is 800, 1019, and again divided by 2 it is 4095, and again it is 4095, and it is divided by 3, then it is 130, 1365, and it's again divided by 3, it is 455, and it is now divided by 5, then it is 91, and it is now divided by 7, so it is 13. So we have factorized 32,760 as 2 into 2 into 2 into 3 into 3 into 5 into 7 into 13 as a product of prime. 32,760 is equal to 2 power q into 3 square into 5 into 7 into 13 as a product of power of prime. Let us try another number, say 1, 2, 3, 4, 5, 6, 7, 8, 9. This can be written as 3 square into 3803 into 3607. Of course, you have to check that 3803 and 3607 are prime. Try it for several other natural numbers yourself. This leads us to conjecture that every composite number can be written as a product of power of prime. In fact, this statement is true and is called the fundamental theory of arithmetic because of its basic crucial importance of the study of integers. Let us now formally state this theorem. Theorem 1.2, Fundamental Theorem of Arithmetic. Every composite number can be expressed factorized as a product of prime, and the factorization is unique apart from the order in which the prime factor occurs. And now Carl Friedrich Gauss, 1777 to 18,055. An equivalent version of the theorem 1.2 was probably first recorded as proposition 14 of book 9 in Euclid's Element. Before it comes to be known as the fundamental theory of arithmetic, however, the first correct proof was given by the Carl Friedrich Gauss in his Carl Friedrich Gauss is often referred to as the Prince of Mathematicians and is considered one of the three greatest mathematicians of all times, along with Archimedes and Newton. He has made fundamental contribution to both mathematics and science. The fundamental theory of arithmetic says that every composite number can be factorized as a product of primes. Actually, it says more. It says that given an composite number, it can be factorized as a proof of prime number in a unique way, except for the order in which the prime occur. That is, given any composite number, there is one and only one way to write it as a prime of product of primes. As long as we are not particular about the order in which the primes occur. So, for example, we regard 2 into 3 into 5 into 7 as the same as 3 into 5 into 7 into 2, or any other possible order in which these primes are written. This fact is also stated in the following form. The prime factorization of a natural number is unique except for the order of its factors. In general, given a composite number x, we factorize it as x is equal to p1 multiply p2 up to n, where p1, p2 up to n are primes and written in ascending order. p1 is equal to or smaller than p2, same as up to p9. If we continue the same primes, we will get power of prime. For example, 32,760 is equal to 2 multiply 2 multiply 2 into 3 into 3 into 5 into 7 into 13.
is equal to 2 power q multiplied 3 power square multiplied 5 into 7 into 13. Here multiply and okay. Once we have decided that the order will be ascending, then the way the number is factorized is unique. The fundamental theory of arithmetic has many applications both within mathematics and in other fields.